In this video, we are going to look at the formulas for derivatives of logarithmic functions and also exponential functions. This slide has all of the formulas that you will want to know, and the first three are actually the main ones to consider, this first column, because this one we already learned. We learned that the derivative of e to the x is just e to the x. But everything that's to the right of that first column are extensions of these derivatives taking the chain rule into account. So if we look at, let's say, this first one here, the only difference here is that we're not taking the derivative of a function that has an x in it. So by the chain rule, we've got to tack on the derivative of the function that's that the log is being taken of with respect to x. So again, everything over here are extensions with the chain rule. I'm going to prove the three formulas in the first column and then give examples for each one. So the first one that we're going to be looking at is to show that the derivative of the function natural log of x is equal to 1 over x. So we're starting with y equals natural log of x. That's our function that we're defining. And I'm using the fact that we can change logarithms into exponentials. When we have natural log, we don't write it, but the base is e. So rewriting this into its exponential form, I can write it as e to the y power is equal to x. So then I'm going to use implicit differentiation and just take the derivative directly of this new equation. So the derivative of the left side should equal the derivative of the right side. We just said that the derivative of e to the x is e to the x. So here we'll have e to the y, but by the chain rule, we have to tack on the derivative of the exponent here, the derivative of y with respect to x. And then the derivative of x on the right-hand side is just 1. Solving for dy dx, we get 1 over e to the y. And then looking back at the original way that we defined the function, we'll make an exchange there and we'll say that the derivative is going to be 1 over x. So that's the proof of the first one. And as I said before, the other two, this one and this one, are just extensions using the chain rule. This would be if I have a different variable that I'm taking the log of, and this would be if I had a complete function. So we put the derivative of that function in the numerator, and then the function goes down below. We'll do a couple examples like these next. So example. Let's let our function be the natural log of x cubed plus 1. When I take the derivative with respect to x, based on the formula, I'm going to create a fraction where this becomes the denominator. So 1 over this. And then I'm going to multiply by the derivative of what's inside the parentheses. So the derivative there is 3x squared. So I'm getting 3x squared divided by x cubed plus 1. Again, the simplest way to think about this is take the function that you're taking the log of and it goes down in the denominator, and then the derivative of that function goes into the numerator. Let's do another example. Let's let y equal natural log of sine of x. Then the derivative will be, based on what I was just saying, I'm going to write the function that I see that I'm taking the log of down in the denominator. So I'll write sine of x here. And then the derivative of what I'm taking the log of goes into the numerator. The derivative of sine of x is cosine of x. And we know from our trig identities that cosine over sine is the cotangent. All right, so let's now look at different log. Of course, this first one was log base e, but now we'll extend this and look at log of a different base, any other number. And the formula is kind of similar in that we're going to have this 1 over x, but we're also going to multiply by the log of whatever the base number is. So I want to start by showing the proof of that, and then I'll do some examples. So we want to find the derivative of log base b of x. We know that by the change of base formula, something that is used not very frequently anymore, we can rewrite a log with any base as a ratio of logs with the same base number. In this case, I'm going to choose natural log, ln of x over ln of b. The number that you're taking the log of goes up into the numerator, and then the base goes down into the denominator. This formula was used a lot when we had, because on calculators, you really only have the options of log, well, not anymore, but we used to only have log base 10, and then also log base e, which is the natural log. And so if we were given a problem with, say, log base 7, we would rewrite it as log of 5 over log of 7, or natural log of 5 over natural log of 7. As long as the base was the same, we could write it in this ratio, and then we could enter it into a calculator. But for our purposes, we're going to use this change of base formula for the proof. Get rid of this. So I'm going to rewrite this as taking the derivative of natural log of x over natural log of b. Now I'm going to use the quotient rule. So I have whatever's on the bottom, natural log of b, times the derivative of the top. We just saw that that was 1 over x. So I'll write this here. This is the bottom times the derivative of the top minus the top, that's natural log of x, times the derivative of the bottom. Now this part is a little tricky because I'm going to write a 0 here. B is just a number, and when I take the natural log of that, I will also get a number. So when I'm taking the derivative, I'm just taking the derivative of a constant, and we know that the derivative of any constant number is equal to 0. So again, natural log of b is just a number, so when we take the derivative, we get 0. So again, we're in the quotient rule, bottom times the derivative of the top, minus top times the derivative of the bottom, all over the bottom squared. Okay, so let's simplify this. I have 1 over x. I guess I'll just write it the way that it is here. Natural log, well, let's see. This is all going to go away. This is 0. And then I have 1 natural log b that's going to cancel with that, but I'll still have 1 left in the bottom. So I think I'm going to have 1 over x, and then that whole thing's divided by natural log of b. And then just rewriting this with the x in the denominator, I get 1 over x times the natural log of b. And that's the formula. So let's do an example problem now. Again, we're going to use this in the example I'm going to do. The one that I proved was in the first column here. And this is just an extension that if, because I'm taking the derivative with respect to x, if I have something that is a function not of x, I have to tack on the derivative of that function onto the end. That's the chain rule. So that's that's the example that we'll do next. So let's let y equal log of 2 plus sine of x. So the derivative is we take the function that we see and we write it in the denominator, 2 plus sine of x. And then I multiply by the natural log of whatever the base is. When we have the common log, this is called the common log. When no number is written, it's implied that there's a 10 here. So we're taking the natural log of 10. And then we have to multiply by the derivative of what I've highlighted there in green, of what the function is inside the parentheses. The derivative of 2 is just 0. The derivative of sine of x is cosine of x. So it looks like I have cosine of x in the numerator. I'm going to put, I'll just put this in parentheses. I'll leave it like that rather than multiplying it out. Natural log of 10. And that's our answer. Pretty easy. Let's do another example. Let's do log of square root x. So I'm going to take the square root x and write it in the denominator. And then I'll multiply by the natural log of 10. Again, this is base 10. But then I also have to multiply by the derivative of what I'm taking the log of. So if we have our function, let's just call it f of x equals square root of x, or x to the 1/2 power, then the derivative there is 1/2 x to the negative 1/2, or 1 over 2 times the square root of x. So I'm going to put that here. So again, I've got to tack on the derivative of the function that I'm taking the log of. Notice that I have 2 square root x's that are going to combine to be a single x. So I'll have 2 times log of 10 times x, and that's in the denominator. So this is my final answer. All right, and then the last proof that I'm going to show you is for an exponential function, not e to the x, because we already talked about that one. We did this one already in class. This would be if I have a base other than e that's raised to the x power. Again, this one being just an extension with the chain rule. So like if I had 5 to the x or 7 to the x, something like that. So we are going to let our function, we're trying to find the derivative of b to the x. So we're going to do a little side work first. There's a fact that we're going to use, and I just want to prove it to you. The side work is to show you that if I write e to the natural log of b, that is equal to b. And that's a fact. I just want to show to you that it's true. So this is kind of like our mini proof on the side. So let's let y equal what's up in the exponent, natural log of b. Rewriting this as an exponential, I can write it as e to the y power equals b. So looking at this, we're starting here now. E to the natural log of b is the same as e to the natural log of e to the y. What I did was now I used this substitution. Instead of having b, I wrote e to the y. And we have a rule with logs that when we have, we're taking the log of something that an exponent is inside the parentheses, we can bring that exponent down to the front. That's one of the properties of logarithms. So I'll bring the y down into the front. So I've got natural log of e. Now, natural log and e are inverses of one another. So this right here is equal to 1. So what I have now is just e to the y, and looking back here, that's equal to b. So again, what I just showed is that e to the natural log of b is equal to b. So this was the fact that we were trying to prove, which we did, and we're going to use that in our proof, in our main proof in just a second. Okay, so back to what we're trying to do. We're trying to find what the derivative of b to the x is. So the first thing I'm going to do is rewrite b to the x. I'm going to go backwards here. I'm going to write b as e to the natural log of b power. So hold on for just a second. Derivative of, okay, instead of writing b, I'm writing e to the natural log of b. This is the part we just proved, but this whole thing is still raised to the x power. So I did the exchange I did was this equal to this. Okay. When you have an exponent raised to an exponent, you multiply the two items together. So for example, if I had 2 to the third power to the x power, we would write this as 2 to the 3x. The exponent and the exponent get multiplied. So that's what I'm going to do. I'm going to multiply the natural log of b and the x together. So e to the natural log of b multiplied by x. We know that the derivative of e to anything is e to anything. So we already know how to take the derivative of e to something. It's going to be e to the natural log of b times x. But then we're going to tack on the derivative of the exponent. That's the chain rule part. So I'm going to do first times the derivative of the second plus the second times the derivative of the first. The first function is natural log of b. the derivative of the second function is 1. The second function is x, and the derivative of the first function, remember we said this before, the derivative of a log of a number is just going to be 0 because it's a constant. So e to the natural log of b times x, and then this is natural log of b. And then, final step is to convince you that this is b to the x. So let's break this down for a second. I have e to the x times natural log of b. I'm just rearranging them so that I can show you that I'm going to bring this up as an exponent here. So this is e to the natural log of b to the x power. And again, because e and natural log are inverses of one another, we're just left with what's here, which is b to the x, and that's what I wrote here. So this proof is using a lot of properties that we learn in algebra, and we don't use them very often. They're used mostly for these proofs. Again, you guys are just going to keep the formula sheets with you and use them as necessary. So let's do an example problem, 2 example problems. The easiest one is just saying, what's the derivative of 5 to the x power? We take, looking at what we have right up above, we're going to write 5 to the x, and then we're going to tack on the natural log of the base, which is 5. Done. That's it. What if we have something a little bit more complex, like 10 to the x squared power? Well, we write the exponential just as we see it. We tack on the natural log of the base, which in this case is 10. And then, because of the chain rule, we have to multiply by the derivative of what is up in the exponent, which in this case is going to be a 2x. So putting the numbers together, I would have 2 times the natural log of 10 multiplied by x, and then multiplied by 10 to the x squared. So this is our final answer. All right, we will do more examples in class. Thank you for watching, and I'll see you in class.